All right, this video is about multiple regression. Multiple regression is probably the most underutilized but most powerful tool that we have available to us. It is one of the coolest things that has ever been created because of what it can do. So consider for just a moment the factors that lead to predicting college readiness. Assuming that there is an actually dependent variable called college ready that actually correlates with students being successful in college, if we consider that college readiness. I still have questions about what we are calling this, but for now we're going to assume it's accurate. So there's some things that go into defining this. All of being college ready, it really is a 12-year journey. So there's reading ability, and a lot of that shows up in third grade. There's some evidence that indicates that if you're on grade level in third grade, you're probably going to be on grade level throughout. If you're not on grade level, you'll forever be behind. Math ability, kind of the same thing. And of course, the reading ability in some ways is connected to the math ability. Your socioeconomic status, the school that you go to, the quality of the teachers, how much money we spend on education. There's a wide variance in the amount of money that is spent on dollars per child. So there's a lot of things, and this is a very short list that go into that. And all of those variables are correlated to one another. As I said, these two things are connected together. This is connected to these two things. This and this are connected together. And actually, how much money we spend on education has something to do with the quality of schools. In some cases, may be the quality of the teachers. So they're related to one another. The SES, socioeconomic status, correlates to all these. Poor schools don't spend a lot of money on it. They tend to have lower math ability, reading ability, and that doesn't mean that they do all the time. But they're all connected. There are good schools or not so good schools that create variation in performance. In that performance, in this case, this dependent variable is college readiness. But they don't relate to each other in the same way. They don't have the same level of correlation. And just because they're correlated to one another, that doesn't mean that there is significant correlation. There's other things besides this list that influence college readiness. Some of them we know, some of them we don't. Some of them we know, but we don't have a way of measuring them. So that is the purpose of multiple regression. It is used to predict some dependent variable by combining and weighing multiple independent variables. So as a brief example, there is a dependent variable of weight loss. There are things that go into that. Some of that has to do with the amount of exercise. Some of that has to do with an attitude towards exercising in the first place. This also has to do with food intake. But the amount of exercise that you participate in also influences your food intake. In theory, if you exercise a lot more, you're going to eat a lot more. But that doesn't necessarily mean that you're going to become heavier. So if you take, for example, an Olympic swimmer like Michael Phelps, I think he consumes 6,000 to 8,000 calories a day. I was reading an article a while back about lumberjacks back in the early 1900s when they were doing everything by hand. They were eating 10,000 calories a day, but there weren't any overweight lumberjacks because their food intake was being outweighed by the amount of exercise. So these things are connected together. These are connected together, and they go not the same amount, but they go together to influence weight loss. This is a specific example called path analysis. This is what multiple regression can do. So you come up with a formula, and in these formulas, what you'll see in the examples I want to provide is there's some dependent variable we're going to call y. And these others are added together in terms of their weight. Sorry, that's supposed to be a plus. Give me just a second. Okay, sorry, this is called a beta weight. So this is like a constant that you add in. So each of these variables go together. So going back to weight loss, this might be Y. Our attitude towards exercise, the amount of exercise we participate in, plus the amount of food intake, plus some other constant is what drives this factor called weight loss. And these are not weighted the same. As we saw, these have different weights. So this is the basic premise of a multiple regression. So we're going to use an example here. And this came off of the internet. We want to assess the association between body mass index and systolic blood pressure using data collected in examination of the Framingham offspring study, whatever that was, at 3,500 participants. The average systolic blood pressure was 127.3. There's a standard deviation. The BMI was 28.2, standard deviation. So they ran what's called a simple linear regression. And basically what they said was if you wanted to predict the systolic pressure, you take the BMI, you multiply it by 0.67, you add 108.28, and that is what your systolic pressure is. So in this example, if you were to take a BMI of 28 and you multiply it times 0.67 and you add 108, you get a systolic pressure of 126. That's pretty close. So that's a very simple version of this. So let's look at a little more complicated one, because what they thought was there's more to it than this systolic pressure. It's not just the BMI that's influencing that. There's some other factors. So now they decided to assess age, gender, treatment for hypertension, and try to account for those through multiple linear regression. So they coded hypertension as a yes, no, gender as a 1, 0, and they added those in. So now they have this equation that has BMI, age, gender, treatment for hypertension. So what you do is for any individual, you take whether or not they're experiencing hypertension, yes, no, their gender, their age, you multiply it by these, take their BMI, add the constant, and that's will predict the systolic pressure. But what I want you to notice about this is look how much of this constant we got rid of. This was 108. The way that we got rid of this constant is we were able to account for more of the variables that influence the systolic pressure. We don't have to allow so much to fluctuate because now we're defining that. That's really the power of that. So we dropped the difference between the BMI and systolic blood pressure is smaller after adjustment for age, gender, and treatment. And what that also means is that the BMI stays significantly associated with systolic pressure. So not only were we able to reduce our constant, go back to this formula, this was the constant for this was a 0.67. Now it's a 0.58, and we lowered that because we defined these other variables. That's a pretty powerful thing to be able to do. One of the other factors that emerges from this data is something called explained variance, and we talked about this in the correlation studies. When we created the model where we're gathering multiple pieces of information, we hypothesize that they relate to one another and define the independent variable. We don't know all of them, and some of them don't matter. So the variables that we know and those that matter are something called explained variance, and that's not defined up here. This is going to be another table. This means our model can explain 46% of the variance in the dependent variable. I'll give an example. I have a doc student who works for WFISD, And she did this for college readiness, the percent of college readiness in a given high school. And she's able to explain 96% of the variance in how many students, or the percent of students who reach college readiness in a high school. The rest is unexplained variance. This is, I've never seen that happen before. So I'm going to show you what that looks like. So this student this is all TEA data from PEIMS. These are all the high schools in Texas listed going down. And across the top, our variable is the PEIMS data that we were able to collect. So this is percent of Black college-ready graduates. And there's a lot of these. This thing, sorry, oh, there we go. The percent of Asian students, percent of bilingual students, et cetera, et cetera. This goes on and on and on. So she ran a regression model. And what she came up with is a list of the things that matter. So she started out, I think there was 456 variables. And she reproduced the 19 variables that matter in relation to predicting the percent of college-ready students. That's 91% of the variation. And these are the things that matter. It's not that the other ones don't matter. These are the most significant ones. So that is incredible to be able to do that. And you can't figure out what those variables are without running that. So I'm going to provide an example of a regression and then provide an exercise for you as well.